Namaste. In the previous learning dialog video, I have discussed about transposition cycle. Okay, so to get the unbalanced voltage at the receiving end, we are trying to transpose the conductors at uniform distances. Okay, so in this learning dialog video, we will consider that such a transposed line, and we will try to calculate the inductance of a three-phase line in such case. Okay, so first of all, we'll start with conductor A. Conductor A, and now let us calculate the flux linkages of this conductor A when it is in position A, position 1, position 2, and position 3. Okay, for example, if you consider the flux linkages with respect to this conductor A when the conductor A is in position 1, the expression for flux linkages can be written as 2 into 10 power minus 7 into current IA, that means flux linked because of the current, its own current passing through the conductor A is IA natural logarithm 1 by RA dash, okay, so self distance, plus now because of the current flowing through the neighboring conductor, that is B conductor. Okay, what is the flux link with conductor A because of current flowing through conductor B? Okay, so that's going to be IB natural logarithm 1 by D12. What is D12? It is the distance from second conductor to the first conductor. Okay, similarly, the flux will also link with conductor A because of current flowing through the conductor C or conductor C. So it's going to be IC natural logarithm 1 by D31. Okay, so D31 is the distance from conductor C, which is in position 3, to the conductor A, which is in position 1. Okay, so this is the flux linked with conductor A because of the currents IA, IB, IC flowing through all the three conductors. Okay. Now, when you move on to the second section, what happens is the conductor A will take the position 2, and conductor B will take position 3, and conductor C will take position 1. So in that case, you need to write this flux linkage equation once again, and you think about it and try to jot down that equation in your notebooks. Okay, so you can take some few seconds to jot down that equation. Try on your own. Okay, so I hope at least few people might have already written the expression for lambda A2. Okay, now it's going to be lambda. We are calculating the flux linkage with current, conductor A only, but now the position got changed from position 1 to position 2. So now it's going to be lambda A2. Lambda A2. So lambda A2 can be written as 2 into 10 power minus 7 into the current IA natural logarithm 1 by RA dash, that remains same. What about IB? It is because of IB. That means when your conductor A is in position 2, conductor B is in position 3 now. Okay, just you can, if you want, you can see this diagram. Okay, so conductor B is in position 3 now. Okay, so it's going to be 1 by, what is the distance? 3, 2. Earlier it is 2, 1. Earlier it is 2, 1. Now it become 3, 2. Okay, so the equation now will get modified as IB natural logarithm 1 by D23. Okay, because the conductor A is in position 2 and conductor B is in position 3. Okay. Similarly, due to current IC that is flowing through conductor C, the flux linked with conductor A now will become IC natural logarithm 1 by D12. Okay, what is this one? The conductor C is located in position 1 and conductor 2 is conductor A is located in position 2. That's why it is IC natural logarithm 1 by D12 Weber turn per meter. Similarly, now when this particular conductor A move to position 3, then it's going to be B will move to position 1 and C will move to position 2. Okay, so in such case, the equation you can now we can easily write. After writing these two equations, you can easily guess the equation is going to be like this. Okay, so because of IA it is 1 by RA dash, it remains same because of self current. Now IB it is natural logarithm 1 by D13 and IC it's 1 by D23. So now if you want to calculate the total flux linkage, you need to take the average. Okay, so it's going to be lambda A. If you want to calculate the average flux linkage of conductor A, then it's going to be lambda A1 plus lambda A2 plus lambda A3 by 3. And if you substitute lambda A1, A2 and lambda A3, and if you simplify, you will get this expression. Okay. So now again you can make use of your KCL, which is current law, where you can write IA plus IB plus IC as 0, and from that you can have this equivalent. IB plus IC is equals to minus IA. IB plus IC is equals to minus IA. So you kept IB and IC, they are similar. So if you take this natural logarithm term common, it will become IB plus IC. And in that IB plus IC, you can substitute this minus IA. That the entire equation will be IA natural logarithm 1 by RA dash minus IA natural logarithm 1 by D12, D23, D31 whole power 1 by 3. Okay, so the equation will get reduced and that will get modified as if you combine those two terms where you have IA as common and simplifying the natural logarithms. Okay, then the equation for lambda A will become 2 into 10 power minus 7 IA natural logarithm D12, D23, D31 whole power 1 by 3 divided by RA dash. Okay. So you can, if you consider this D12, D23, D31, it's like mutual GMD, and this is like self GMD. RA dash is like self GMD, and this is cube root of D12, D23, and D31 can be considered as mutual GMD. Okay, we are getting the similar equations like what we have already seen. So here we are simplifying the equation by considering this product or cube root product D12, D23, D31 as D equivalent. Okay, so it's we are calling it as equivalent equilateral spacing. Equivalent equilateral spacing. Okay, so then the expression for LA will become 2 into 10 power minus 7 natural logarithm D equivalent by RA dash, and that is equals 2 into 10 power minus 7 natural logarithm D equivalent by RA dash Henry per meter. Okay, so this is the expression for LA. Now similarly, if you assume this RA and RB and RC, then what happens is this LA and LB and LC also become equal. Okay, so all the three inductances will become equal. Okay, if you assume this RA, RB and RC, because in the numerator we will have only this D equivalent term. So these inductances LA, LB, LC will become equal, and this equation can be further simplified, and you can write. So if the spacing is equilateral, then D equivalent will become D. So if uh, this is one equivalent, and if this distances are equal, D12, D23 and D31 are equal, then what happens? It will become cube root. Since it is cube root, D equivalent will become D. Okay, if you assume D12 equals to D23 equals to D31 equals to D, then it will become D power D cube whole power 1 by 3, and that will be come D. Okay, so if it's a equilaterally spaced case, then it's going to be D equivalent is D, and once again the entire equation will reduce to LA, which is 2 into 10 power minus 7 natural logarithm D by RA dash Henry per meter. Again, if you consider this radius of the three conductors are equal, then it will become LA equals to LB equals to LC. So this is how you can calculate the inductance of three-phase lines. So in this learning videos, we have started with single conductor, then we have gone for bundle conductors, and then we have considered a single phase case as well as three-phase case also. Okay, so the calculation of inductance for three-phase lines is over. Thank you.